is entitled Multi-Material Topology Optimization of a Permanent Magnet Synchronous Motor.
Yes.
The floor is yours.
Yeah. Can I start? Yeah, okay. Hi, hello everyone. My name is Lingfeng Gao, and I'm a PhD student in the Department of Mechanical Engineering at Stony Brook University. So today, the topic of my presentation is multi-material and nonlinear topology optimization of the permanent magnet synchronous motor. So this is my printed outline. So I will start with the motivation and background and the design permanent magnet synchronous motor and shape and topology optimization of the PMSM and the computational result and verification and current and future work. Okay, I'll start with the introduction and motivation. So the rare earth material has been widely used in many high devices and applications and clean energy applications due to their unique electronic properties, magnetic and optical properties. So you have various applications such like the catalyst and glass manufacturing, electronics, ceramics, metal alloys, and permanent magnets. So the rare earth material play a crucial role in advancing the magnet technologies, particularly in design and function of the electric machinery. So as society transition further into the electrification following the Industrial Revolution, so the demand of renewable energy has been grown significantly and rapidly. And the electric machinery, which is include the motor and generator, which rely heavily on the unique properties of the rare earth material to achieve the unparalleled efficiency and power-to-weight ratios. So electric machinery are widely used in various aspects in our daily life. For example, the wind turbines and the electric generators, the water turbine in hydropower, and an increasing number of the electric vehicles. So the permanent magnet is so good in electric machinery, but there still have some limitations. The first one is the supply chain is unstable. I don't want to talk more about this part. And the second part is the prices are continuing to increase. So because we have collaboration with General Electric, based on the data General Electric provide to us, the cost of the permanent magnet in one offshore wind turbine is almost like $1 million. And if you got a chance to visit the London, New York, you can see there's a large amount of the offshore wind turbines in the ocean side. And the third part is the environmental impact, and the fourth part will be recycling and recovery challenges and design limitations. So there are a lot of electric machine companies that are trying to reduce the rare earth material usage because it can bring some benefits like lower the cost, reduce weight, and increase design and space and freedom. And the fourth thing is improve the performance and enhance the thermal operating efficiency. So they are seeking for some new technology and tools which can reduce the rare earth material usage without sacrificing performance. So here's the solution. We're going to use topology optimization here. But before I dive into the topology optimization, I will first talk about the design permanent magnet synchronous motor. So what is a permanent magnet synchronous motor? So a PMSM is a brushed electric motor that uses a permanent magnet rotor and a wounded stator to generate a rotating magnetic field. So that's a very classic PMSM. We have the yellow part is coil woundings, and the blue and the red part is the permanent magnet, and the light gray part is the soft ion, and the light blue part is the air. So a PM motor, which the magnetic field from the rotor rotating synchronously with the magnetic field generated by the stator. So that's why I call it a synchronous motor. And the interaction of the rotor and stator magnetic field generates the net torque, which is able to convert winding currents into a mechanical power. Yeah. So permanent magnet offers several advantages. For example, it's high efficiency, high power density, high torque to inertia ratios, and wide speed range, and some other advantages. So which make them popular in various applications such as electric vehicles, automation, and soft robotics, and clean energy systems. So here's the bonding conditions of the PMS. So we have the very classical 8 poles and 48 slots permanent magnet synchronous motor. In order to reduce the computational cost, we only consider about the one sector of this PMS, and we apply the anti-parallel bonding condition at both sides. So you can see the red, blue, and the green color, which represent the surface current. So each of them differ by 120-degree electric angle. And this is a finite element simulation of the reference model or initial model. So we can see the peak value of the remnant flux density is around like 2.33 Tesla. Sorry, 2.3 Tesla, and the net torque is around like 160 Newton meters. Oh, what's going on? And we can see the torque plot shown here is offers a it's okay, and offers a regular torque ripple. So next step, I will focus on the shape and topology optimization of the permanent magnetic synchronous motor for improving the torque characteristics. So I believe most of you guys are very familiar with topology optimization, which is the numerical tool that optimizes basic material layout within a given design domain. So the challenge is the structure of the electromagnetic system is it's highly dependent on the designer's intuition and experience. So these are some classical examples of the topology optimization. So the performance of the electric machinery can be measured as a yes. Just let's break it down. Okay, no worries. So the performance of the electrical machinery can be measured as the electric field distribution, system energy, system power, and force and torque, and something else. An example of the design objective can be the improving the device performance, obtaining a desired distribution of the magnetic field, and obtaining a desired inductance. So what are the challenges of the topology optimization in the electromagnetic system? So I have a question here. So what are the differences between topology optimization in electromagnetic system and other systems? So the answer is the electromagnetic field exists even in the vacuum. So the magnetic fields like stress, strain, and fluid velocity does not exist only where the medium exists. So for example, there's no Young's modulus, no stress and strain in the air. So the topology optimization in the electromagnetic system is in fact a multi-material problems. So here's the reference model showing on the left, and the sector reference model showing on the middle, and the blue part is our design domain in the rotor core. So here I would like to talk about the multi-material topology optimization interpolation. We usually distinguish material based on their different material properties. So there are two crucial material properties of the electric magnetic systems. So the first one is the remnant flux density Br, and the second one is the relative permeability μr. So what is relative permeability μr? Which means, for example, the air has a very low relative permeability, and which means it provides a very high resistance or reluctance of the magnetic flux. So the magnetic flux will tend to avoid passing through this air region in order to passing through some other region with a higher relative permeability, like soft ion. And the remnant flux density means the level of the magnetic flux density remains in the magnetic material after the external magnetization has been removed. For example, if this material got higher Br, so that means it will be hard to magnetize and demagnetize. So for the soft ion, they got lower Br, so which means it's easy to magnetize and demagnetize. So the method over here, we're using a density-based method, which is easy to implement, and these two functions, μr, Br, is our interpolation functions. We have two artificial densities. The one means the material, and the other means the void. And here's our object functions. We are trying to maximize the average torque and minimize the volume ratio of the volume fraction of the permanent magnet. And this object function is subject to three constraints, which is the volume constraint, performance constraint, and the governing equation of the magnetostatic problems. So here's an animation of the evolution. So we can see the right arrow is swinging during the optimization. So at this moment, we not only optimize the material distribution of the electrical machinery, but also optimize the magnetization direction simultaneously. Let's say it one more time. You can see the right arrow is swing during the optimization. And the dark red part is the permanent magnet, and the green part is soft ion, and the blue part is the air. Yeah, so that's the initial design, and that's our optimized design. So let's do a verification of this optimized design. So this is a final element simulation based on the optimized design. So we can see the peak value is about like 2.4 Tesla, and the torque, average torque is around like 380 Newton meters. Let's do a comparison here. So for the initial design and optimized design, they got the same volume ratio, but the performance is almost 2 times than the initial design. 2 times than the initial design. And that's the initial design, and that's optimized design, the full model, and that's the 3D model. And the center part, the gray part is the shaft, which is transfer the power out of the motor. Yeah. And last part, I would like to show some of our current and future works. So in our lab, we focus on topology optimization, especially the level set-based method, which is using a higher dimensional function to represent the 2D design domain. For example, this 5 represents the level set function, which is larger than 0 represent the material region, equal to 0 represent boundary, and less than 0 represent the volume domain. And the level set-based method can bring some advantages like ensure a clear boundary, and it can provide a precision and accurate optimization solution, and easy to handle topological change. And the evolution of the boundary dynamics is governed by this Hamilton-Jacobi equation, and the Bayesian can be calculated by the sensitivity analysis. So here's some work done by our lab. So the first one is the topology optimization of the permanent magnet for generators using level set-based method. We can see that's the evolution of the optimization. The red part represents the permanent magnet, and blue part is air. And this one is nonlinear shape and topology optimization of the synchronous reluctance motor, which is covers the multi-physics and material nonlinearity into consideration. And then now our ongoing work is using level set-based method to do the topology optimization of the permanent magnet synchronous motor. And our software have already achieved about like 10% reduction in one of the GE offshore generators. Yeah. So after I finish the permanent magnet synchronous motor optimization, so we can build a full solution for the electromagnetic systems. Yeah, that's a reference. So yeah, I'm ready for comments and questions. Go ahead.
Just curious, are there any structural concerns of flying apart under centrifugal force or weird vibration effects? Such a strange geometry?
Good question. At this moment, for the permanent magnet synchronous motor, we not consider about the other physics. We only consider about the electromagnetic the concerns. But for this one, the synchronous reluctance motor, we consider the centrifugal force of the structure. Yeah. Yes.
So this might be a really dumb question because this isn't my field.
Yeah.
You chose to use the 8 sectors.
Yes.
And then you just chose one and worked with it. What happens if you took? Is there any sort of interaction between the sectors?
So that's why we apply the anti-parallel bonding conditions. So, for example, this magnet pole is 2 north pole, and the anti-parallel bonding conditions. So the next sector will be the south pole. Yeah.
Okay.
In order to reduce the computational cost. Yeah. Yeah.
We have some weighing factors, right? Like weighted factors. So are these predetermined weighted factors, or like it's also part of the optimization process?
Sorry, I didn't understand your question.
You had some weighted factors, right?
Yes.
W1, W2. So are these predetermined factors, or is it part of your optimization?
Part of optimization.
Part of, yeah. But you do have some bounds, right?
Yeah.
So why?
Sorry. Yeah.
So why you choose the eighth sector to do run simulation? Is eight any reason?
It doesn't really matter. That's just a reference model. So we just choose. So we have the various reference model. So it's not just 8 posts, 48 slots. It can be some other like 6 posts and 36 slots. Yeah.
So that
it doesn't really matter.
The same result in the topology?
Not the same. Not the same. Because different machinery, they have the different design domain, different size of design domain, and the boundary condition they might same, but just the design domain is different.
So the number of polar is a parameter in your or in your?
No, it's not the parameter.
Okay, now how do you make sure which you choose the eighth pole polar, and it gives you the best result compared to other numbers?
It's hard to tell. So I cannot guarantee this is the local optimal or global optimal. So just I would say this is optimal design in this based on this kind of like boundary conditions. I would say. Yeah.
So what software you use?
Right here we're using the console multiphysics.
How about the optimization? What do
optimization? We as this example we use the density-based method which is embedded in the console multiphysics. But for our current and future works, we usually write our own code to do the optimization.
You use your own code as a plugin for console.
Yeah. We only try to export the final result from the console.
So, what kind of algorithm you're going to be using?
Level set-based method. So, yeah.
Have you considered manufacturability and any constraints that come with it in these topology optimization studies?
No, we not consider manufacturability, but that's a big problem actually. So in the future, we'll definitely take them into consideration. Yeah. Any more questions? So if no more questions, so I'll stop here. Thank you, everyone.